sklearn semi-supervised label spreading. Description label spreading is a semi-supervised learning algorithm that propagates labels from labeled data points to unlabeled data points based on the similarity between them. It operates by constructing a graph where nodes represent data points and edges represent the similarity between them. The algorithm then iteratively spreads the labels of labeled points across the graph, influencing the labels of unlabeled points based on their connectedness. This method is particularly useful when dealing with datasets where only a small portion of the data is labeled. X. This is the feature matrix representing the data. It is a 2D array where each row corresponds to a data point and each column corresponds to a feature. Y. This is the label vector, which provides the labels for the labeled data points. The length of this vector should match the number of labeled data points. Labels. This is the predicted labels for all data points, including both labeled and unlabeled data. This is a 1D array of the same length as the number of rows in X. Transdictive labels. This is a 1D array of the same length as the number of rows in X. However, it only contains the predicted labels for the unlabeled data points. The labeled data points will have their original labels unchanged. Construct the similarity graph. The algorithm begins by creating a graph where nodes represent data points and edges represent the similarity between them. The similarity between two data points is determined by a chosen distance metric, such as Euclidean distance or kernel function. Assign labels to labeled data points initially. The labeled data points are assigned their true labels. Unlabeled data points are assigned an initial label, typically based on a uniform distribution or a random assignment. Iterative label propagation. The algorithm iteratively updates the labels of unlabeled data points by propagating the labels of their neighbors. This process continues until convergence, meaning that the labels of unlabeled data points no longer change significantly. Accuracy. The accuracy of the model is evaluated by comparing the predicted labels of unlabeled data points to their true labels. This metric measures the percentage of correctly classified unlabeled data points. F1 score. The F1 score is a harmonic mean of precision and recall, providing a balanced measure of the model's performance. Decision boundary. A visualization showing the decision boundary separating different classes can be plotted based on the predicted labels. This allows for a visual understanding of how the model is classifying the data. Feature importance. A bar chart showing the importance of different features in making predictions can be useful for understanding which features are most influential. Alpha. This parameter controls the strength of the label propagation process. It represents the proportion of the label information to be used for propagation. Higher values of alpha imply stronger propagation, which can result in more confident predictions but also may overfit the labeled data. Gamma. This parameter controls the similarity between data points. A higher gamma value implies a more localized influence of neighboring data points on the label propagation, while a lower gamma allows for more global propagation. Confidence score. The algorithm can provide a confidence score for each predicted label, indicating the certainty of the prediction. This score can be used to identify uncertain predictions and potentially focus on those data points for further analysis or label correction. Entropy. The entropy of the predicted label distribution can be used as a measure of uncertainty. Data points with high entropy have a more uncertain label prediction. Challenge 1. The choice of the similarity metric can significantly affect the performance of the algorithm. If the chosen metric is not appropriate for the data, it can lead to incorrect label propagation and inaccurate predictions. Sample use case that resulted in challenge 1 using Euclidean distance as the similarity metric when the data has nonlinear relationships between features could lead to misclassifications. Consider using kernel functions, such as the Gaussian kernel, which can capture nonlinear relationships. Experiment with different similarity metrics to find the best one for the data. Challenge 2. The algorithm can be sensitive to noise in the labeled data. Incorrect labels can be propagated to other data points, leading to inaccurate predictions. Sample use case that resulted in challenge 2. A small number of mislabeled data points can significantly impact the overall performance of the model, especially when the proportion of labeled data is small. Fixes to challenge 2. Use techniques for data cleaning and label correction to ensure the quality of the labeled data. Consider using robust versions of the label spreading algorithm that are more resistant to noise.